Do you know who was awarded the first Nobel Prize in Physics and for what discovery? And do you also know that he refused to patent his discovery for the common welfare of society? It was Wilhelm Röntgen who discovered X-rays. And that is what we are going to study in this chapter about the X-rays. Okay, about how it is produced. Okay, and this chapter is going to be a very short chapter. It's a very easy, very short chapter, provided you have understood the earlier chapters, especially the wave particle duality and Bohr's atom, because many concepts from those two chapters we are going to use directly in this chapter. So if you have not completed those two chapters already, then you should do that first and then you should do this chapter. So let's start with X-rays directly. Okay, X-ray. Okay, the first point. Okay, discovered by Wilhelm Röntgen. Okay, who was awarded the first Nobel Prize in Physics in 1901. The first person to be awarded the Nobel Prize in Physics, okay, in 1901. Okay, he discovered X-rays. Now, what are X-rays? X-rays are, first of all, they are EM waves. X-rays are EM waves like light, ultraviolet, infrared, visible light, radio waves. Okay. In the same way, X-rays are also EM waves. They are of same type, exactly same type. X-rays are same as the light that we see. The only difference is in frequency, wavelength, energy, and all that. Okay. So X-rays are EM waves of very short wavelength and consequently very high energy. Okay, from this relation E is hc over lambda. Lambda is very small, so energy is going to be very high. Okay, now what is the range of its wavelength and energy? Range of wavelength. Okay, lambda is from 0.1 angstrom to 10 angstrom. Okay, you understand that we do not really have a clear-cut boundary between different parts of the EM spectrum. So this is just an approximate range. Okay, these boundaries are not fixed. Okay, so this is 0.01 nanometer to 1 nanometer. This is the range of their wavelength. Now, what about energy? Energy we can write it like this. Okay, so this I can write it as you see 1240 nanometer electron volt over wavelength lambda in nanometer. Okay, so if we use this relation, this is the relation that we derived in which chapter? Wave particle duality. So we are going to directly use this in writing the energy here, and this answer I am going to get in electron volt. Okay, so the range of energy E will be, you see, 1240 over 0.01 electron volt to 1240 over 1 electron volt. Okay, now this will be equal to, this is electron volt and this is 0.01. So if I don't have this Okay, it becomes 100 times, 100 to 0 0 here, so 124. Okay, it becomes 124 kilo electron volt to 1.24 kilo electron volt. Okay. This is the range of energy of what? Photons of X-ray. Okay, so this is the quantum of energy. So this is the range of energy of one single photon of X-ray. It's a very high energy, okay. Now the X-ray having this energy, they are known as hard X-ray, and this is a soft X-ray. Okay. Even the soft X-rays have high energy, okay. Now, so this is one general introduction about the X-rays, how they are produced. Okay, they are produced in reverse process of photoelectric effect. Okay, if you reverse this photoelectric effect, then it becomes the production of X-ray. Okay, let's look at one very simple example here. One very simple schematic diagram. It's like this. I have this metal, okay, a metal. Now, on this metal, if photons are incident, these are the photons, okay, h nu. These are the photons. If photons are incident, then electrons are ejected. Okay, so the electrons will be ejected from here. This is known as photoelectric effect. Okay. Now reverse this. Okay. So when electrons are incident, okay. Now if the electrons are incident on this metal surface, okay, they are highly energetic electrons. They are incident on this metal. Okay. Then photons are emitted. Okay, these photons are known as X-ray. Okay, this is how X-rays are produced. Okay, this is just an schematic, just to give you an idea. Now there is an arrangement, a separate arrangement to produce it. Let's look at that arrangement. The arrangement to produce X-ray, it is also known as X-ray tube. Okay, so what I need is to produce X-ray. What I need a highly energetic electron, fast moving electrons, and a metal. Okay, and that's it. I can produce X-ray. So we make some arrangement like this. Let's say that okay, so I have this thing here. We create, first of all, we take a vacuum tube. Okay, this is a vacuum tube. Okay, let me write it here. It's a vacuum tube. It's also known as X-ray tube. Or Coolidge. So Coolidge was a scientist, okay, who made this arrangement, this X-ray tube, vacuum tube, Coolidge tube. Okay, now what I need a source of electrons and a metal. Okay, so we take a metal here. Let's say my metal is in this shape here. This is my metal. This is a metal target. Also, it is also known as target metal. Metal target metal. Okay, both are same. And then, so this is my metal. It's ready to be bombarded with electrons. I need a source of electron. How do I produce electron? How can I produce electron? There are several ways of producing electrons. One is this photoelectric effect. Okay, The other is very simple. If I simply heat a metal, metals have large number of free electrons. If I simply start heating it, electrons are ejected. If electromagnetic wave is incident, then also electrons are ejected. These electrons are known as photoelectrons. Now, I don't have to do this. If I simply heat this metal, okay, then also electrons are ejected. They are known as thermionic electrons. Thermionic, okay, electrons ejected because of thermal effect. Thermionic electron, okay. So I do not really have to make very elaborate arrangement. I can simply, you see, I have this heating coil. This heating coil. If I simply pass current in here, if I simply pass current in here, it becomes heated, electrons will be ejected. And that's it. But now the problem is, when the electrons are ejected from here, they will not move away. Okay? They will just make a cloud. They will just make a cloud. They will remain there. They are ejected, they become free, but then they will remain there. Okay? They will not move very far distance. I want these electrons to hit this target here. I want them to hit it. So what we do is, we apply a potential difference between this metal target here and this heating element here. Okay? So we have to do that, we make this arrangement here. Okay? So now this is we make the arrangement like this. Okay? Such that the electrons which are ejected, they will be accelerated. This is kept at positive potential. So electrons will be accelerated. So this potential here is also known as accelerating potential, V. Okay? This V is accelerating potential. Accelerating voltage. Accelerating voltage or accelerating potential. Okay? What is the effect of that? The electrons will be accelerated. They will gain kinetic energy. Now the electrons are moving through this potential difference from here to here. The potential difference is equal to this potential difference. Okay? So when a charge moves through a potential difference, what happens? When a charge moves through potential difference, its kinetic energy changes. Okay? Its kinetic energy changes. Now, we have discussed this point several times. Okay? So if I have a charge Q accelerating through a potential difference, what will be gain in the kinetic energy? Okay? So if the kinetic energy here is 0, let's say, electrons are just ejected, they do not have much kinetic energy or 0 kinetic energy. Okay? By the time they reach here, now the electrons are getting accelerated. These are electrons. Okay, these are electrons. They are getting accelerated. They are going to hit the target metal here. They are going to hit it. Okay. By the time they reach here, what is going to be their kinetic energy? Okay, kinetic energy here is 0. By the time they reach here and hit the target, they are being accelerated through what potential difference? It is equal to V. This is also known as accelerating voltage. Okay? Then by the time they reach here, their kinetic energy is going to be E times V. E times V. Okay? I hope that you are able to see this clearly. Sometimes this focus gets disturbed. Okay, anyway. So do you see? Now what will happen? This thing will happen. Electrons are now hitting the metal. Okay, then photons will be ejected. Photons will be emitted. Okay, so now from here, the photons are emitted. Okay, these are known as X-rays. The photons are emitted. That's how, in a very simple arrangement, we can produce X-rays. Now what we do? Now we analyze this. Okay, so this radiation is coming out. I want to analyze it. What is the meaning of analysis? I want to find out its wavelength. I want to find whether it is a single wavelength or it is a mixture of wavelength. And if it is a mixture of wavelength, then do all wavelengths have same intensity or different intensity? That means, do all wavelengths are all the wavelengths are coming in same amount or different amount. Okay, so to do that, we carry out what we know as spectroscopy. Okay, we try to analyze its spectrum. Now, to analyze its spectrum, what is the best way and the easiest way to analyze an EM wave? I know that this EM wave contains large number of wavelengths. Okay, I want to find out its constituent. Okay, then the best way is to use a prism. Okay, so if I use a prism here, okay, if I use a prism here, then all of these wavelengths will get separated. The way white light is broken into its components, the same way this collection of wavelengths, different wavelengths, this will also be broken into its components. Okay, so we get something like this. Okay, different wavelengths I find. Okay, so on this photographic plate, I get different lines. Okay, and if we, so this is this tells us the number of wavelengths present. Okay, then what we do, we try to find out their relative intensity. Do all wavelengths are arriving in the same amount? Okay, or they are arriving in different amount? Okay, that means do all wavelengths have same intensity or different intensity? Then we plot the graph, and when you plot the graph, you get a graph, a very interesting graph like this. Okay, this is lambda, and this is intensity. Intensity, that means intensity corresponding to a given lambda. Okay, I get a graph something like this, a very interesting graph, a peculiar graph. Okay, something like this. So first of all I get a continuous graph. I get a continuous graph. That means all the possible wavelengths are present above a certain value, above a certain minimum value. This is lambda minimum. Do you understand what we are doing here? We are analyzing this X-ray to find its constituents. Okay, I want to know about this X-ray, whether it is made up of a single wavelength or many wavelengths. If it is made up of many wavelengths, what are those wavelengths? Do all the wavelengths have same intensity or different intensity? Okay, so when we do that, we get a graph like this. This is lambda versus intensity. Okay, this is a continuous graph. Continuous, that means all the wavelengths are present, but there is a minimum value here, a minimum. I never get a wavelength is smaller than this particular value. This is known as lambda minimum. And then I get many peaks. Okay, these are the peaks. Suddenly, okay, for certain wavelengths, the intensity increases suddenly. Okay, they are known as peaks. Okay, they are known as peaks. Okay, all of these are peaks. Okay, so for a given metal, I am going to get many peaks. Okay, now what do they represent? What is the meaning of this lambda minimum? What is the significance? And what is the significance of these peaks that we get? Okay, so now there are two processes. Let's understand. Let's understand the meaning of this continuous portion, this lambda minimum, and the peaks that we are getting here. Okay, this is lambda 1, lambda 2, and lambda 3. Let's try to understand that. Okay, it's like this. Two processes are involved. Two processes are involved. Okay, first process. Okay, when highly energetic electrons hit the metal, okay, hit the metal, they are decelerated. They are decelerated. Okay. As a result, they lose their kinetic energy and the loss appears as photons. Photons, that is X-ray, photons of X-ray or X-ray. Okay, it's all the same. So I have this solid metal here. Okay, this is the solid metal. Okay, this thing is solid metal. Electrons are bombarded. Electrons are hitting this solid metal. They will try to go inside the metal. As they try to go inside the metal, their motion is impeded. Their motion is retarded. Okay, we say that they are decelerated. Okay, they are decelerated. Okay, so their kinetic energy will decrease. When the kinetic energy decreases, they will emit EM wave. Okay, whenever, this is a very general property. If any charge accelerates, okay, so we have discussed this point earlier also. Let's do that again. When a charge accelerates, then it emits EM wave. Here also the charge is accelerated. What is the meaning of acceleration? Its velocity changes. Acceleration or deceleration. Okay, both are same. Even if a particle is decelerated, in a sense it is accelerated. Okay, acceleration is its velocity is changing, whether it is increasing or decreasing, direction changes, whatever changes. If a charge accelerates, it produces EM wave. Okay, note down this point. Very important. We have discussed it earlier also. Now also we are discussing it. So these electrons are accelerated. They are decelerated. Both are same. They are losing kinetic energy. Okay, and that loss appears as photon or this X-ray. Okay, this is called continuous X-ray. Continuous X-ray. Or there is one other name for this. Bremsstrahlung X-ray. Bremsstrahlung. Okay. This is a German word for braking. German word for braking. Okay, the motion of electrons is braked. Okay, some brake is applied. As a result, they are losing their energy, and that loss, you see, the loss appears as photon. Okay. Now, photons of maximum energy. Okay, that is minimum wavelength. Okay, photons of maximum energy, that is minimum wavelength, are emitted when all of the energy, when all of the kinetic energy of electron is lost. It is lost. What it means? The electrons are losing kinetic energy, and that loss appears as a photon. Okay. In which case I am going to get photons of maximum energy. Maximum energy corresponds to minimum wavelength. Minimum wavelength. Okay. So when all of the energy of electron is converted into photon. Okay. Now what is all of the energy? Energy here is 0. By the time electrons reach here, their energy becomes E times V. E times V. Okay. Then here I will write Hc over E max. I will write like this: E max of photon is equal to kinetic energy of electron. Okay, when all of the energy is converted into one photon, one single photon. Okay, so this will correspond to Hc over lambda minimum. is equal to E times V. Okay, and then I have this lambda minimum. Lambda minimum is equal to HC over EV. HC over EV. In this relation, everything is a constant except V. This is accelerating potential. V is accelerating voltage. Okay, so this lambda minimum, it will depend only on the accelerating voltage. If you increase the accelerating voltage, this lambda minimum is going to decrease. If you decrease this accelerating voltage, this lambda minimum is going to increase. Okay, it depends only on accelerating voltage. All other terms are constant. H, C, E. They are fundamental constants. Okay, it depends only on V. Okay. So now, do you understand the origin of the meaning of significance of this lambda minimum here? It is a cutoff wavelength. Okay, I am not going to get any X-ray, okay, having wavelength smaller than this. Okay, so this part of the wave, this part of the spectrum without the peaks. Also, I have this continuous variation of wavelength. I get every possible wavelength above a certain value, that is known as continuous X-ray or Bremsstrahlung X-ray. That means breaking X-ray. Okay, now what about the second part? That is peaks. Okay. What about the peaks? The second process. Second, when highly energetic electrons hit the atom of target metal, they knock out electrons from inner shells. Interesting. Okay. Now, so electrons are hitting the metal. Okay. Many electrons will directly collide with the atom. Okay. Now, when they collide with the atom, okay, it can knock out some of the electrons. Okay. So they knock out electrons from inner shells, thus and create a vacancy. Now, when that vacancy is filled up by electrons, of the outer shell. Outer, what is the meaning of outer? High energy. Okay, higher energy states. Okay, when that vacancy is filled up by electrons of the outer shell, okay, so the electrons are ejected, they are knocked out, they are kicked out from the inner shell. A vacancy is created. Now that vacancy, if that vacancy is filled up by the electrons of higher shells, outer shells, higher energy shells, okay, is filled up by electrons of higher outer shell, then okay, photons of energy equal to difference are ejected, are emitted. Okay, they are called characteristic X-ray. Characteristic X-ray. Okay, the peaks in the X-ray spectrum correspond to characteristic X-ray. peaks. Do you understand? Understand this? Okay. So it is like this. Let me clean all of this. So continuous and characteristic. Two types of X-rays. They have different origin. They have different regions, different origin. Okay, the continuous and characteristic. So those peaks refer to characteristic X-ray. Now what happens is it's like this. Okay. I have this atom here. Okay. I have this atom. This is my nucleus. There are many shells here. Okay. This is the first orbit, and then the second orbit, and then the third orbit, and then the fourth orbit, and all that. Okay. Now there are electrons here. Okay. 2 electrons here, then 8, 4, 5, 6, 7, 8, and similarly here also many electrons. Okay, many electrons here. So this is the atom of my target metal. Okay. Now electrons are incident. These are the electrons. Okay. Now they collide with this atom and they knock out some of the electrons. So this electron is gone. Okay. This electron is gone. Okay. So this is equivalent to this. Okay. So I have this orbit. This is my nucleus. Okay. So when the electron is knocked out, okay, a vacancy is created. This is the vacancy. Now this is the vacancy. Now this vacancy is going to be filled up. This vacancy is going to be filled up by electrons of the higher shell. Higher shells have higher energy also. Okay. So one electron here is going to fill up this vacancy. Electron here is going to fill up this vacancy. Okay. This is lower energy state, higher energy state. There is energy difference. Okay. So when the electron jumps from this to here, it's okay. So the photon is going to be emitted. Then photon, what will be energy of the photon? It will be equal to the difference. Okay. So this is the photon. This is my K shell. K. The innermost shell, the first shell is known as K. This is L. This is M. This is N. Vacancy is created in K shell. Understand this. A very important nomenclature. The vacancy is created in K shell. It is being filled up by electron in the immediate shell, that is L shell here. Okay. This is called K alpha. Okay. So if the vacancy in K shell is filled up by L shell electron, photon is emitted. We call it as X-ray. Okay, that X-ray, that photon is known as K alpha. K alpha radiation, K alpha photon, K alpha X-ray. Okay, now if the same vacancy is in K shell, if it is filled up by an electron in the M shell here, okay, so if this electron fills up this vacancy, then also a photon is emitted, that will be known as K beta. Okay, this will be K beta. Okay, and if the same vacancy here in K shell, understand, K shell, if it is filled up by an electron here in the KLMNN shell, if this electron fills up this vacancy, then also a photon will be emitted. What will be energy of that photon? Equal to this energy difference. Okay, then also a photon is emitted, it will be known as K gamma. Okay, do you understand this? These are known as a characteristic X-ray. Characteristic X-ray. The first type was continuous X-ray. The minimum wavelength of continuous X-ray, it depends on accelerating voltage. What do you think? The wavelength of these characteristic X-rays, will they also depend on accelerating voltage or something else? Okay. So the energy of these photons here, they depend only and only on these energy differences. They had nothing to do with accelerating potential. Only this energy difference, that's it. And this energy difference depends on metal. It depends on metal. Okay, the minimum wavelength, lambda minimum, in the continuous part of the spectrum, it does not depend on metal, it depends on accelerating voltage. But here, they depend only on the metal. Each metal is going to have a different values for the energy of K alpha, K beta, K gamma. Okay, so this is what happens when vacancy is created in inner shell. Okay, what is the inner shell here? This is K shell. Same way, vacancy can also be created in L shell, M shell, any of the inner shells. Okay, so let's represent all of this in a different diagram, which will be more easy to understand. Okay, it's like this. Okay, it's like this. Okay, so we represent it by a simple diagram. Okay, I can write it like this. This is my K shell here. Okay, this is K shell. This is L, and this is M, and this is N. Okay, and all that. Okay. Now, if the vacancy is created in K shell here, and if that vacancy is filled up by electron of L shell here, okay, then a photon is emitted. This will be known as K alpha. K alpha. Okay, if it is filled up by an electron here, M shell electron. Okay, so here also photon is emitted. This will be K beta, and then from N shell, here also photon is emitted. This will be K gamma. Understand? In all of these, the vacancy is in K shell. Okay. Now, if the vacancy is in L shell, here vacancy is here, it is filled up by an electron here. Okay. Then here also a photon is emitted. Okay. This will be known as, okay, this will be L alpha. Vacancy in L shell being filled up by an electron in M shell, L alpha. Then, if the vacancy is filled up by an electron in the N shell here, okay, this becomes L beta. Okay, it keeps on going. Okay, you understand the nomenclature? Okay, you understand it for K and L, you understand it for all the others. Now, so corresponding to this, we get peak or characteristic X-rays. Notice a few things. Okay, notice few things. What will be relation between, let's just write the K series, okay. What will be relation between the energy of K alpha, okay, will be less than energy of K beta, will be less than energy of K gamma. Okay. It's obvious. It's obvious. Okay. What about wavelength? Okay. Wavelength of alpha. There is an inverse relation between energy and wavelength. Okay. So whatever is the relation here, it is going to be just reversed. Okay. It is going to be more than alpha, lambda of beta and lambda of gamma. Okay. Energy of K gamma is highest. Its wavelength will be lowest. Okay. Now what about L series? Similarly, L series also. L series, I will have in terms of energy. Okay. L beta is more than L alpha. Okay. So correspondingly, wavelength. Okay. It is lambda of beta is going to be less than lambda of alpha. Okay, understood? Now one other thing, K series, L series, lambda, relation, only the relation, okay. Now what about Let me ask you one other question. Okay, let me check if you are able to see this right. Sometimes the focus gets disturbed. Okay, I have to keep on checking it. Anyway, okay, what about K alpha and L alpha? K alpha and L alpha. Okay, what is the relation between their energy? Energy. K alpha here, L alpha here. Can you find out the relation? Can you find out the relation? Okay, which energy is going to be higher? Okay, so this thing we discussed in Bohr's atom. Okay, as we go away from nucleus, as the states increase, as the orbits increase, okay, the energy difference between the subsequent, the neighboring states, it keeps on decreasing. Okay, so energy difference here, okay, between these two cells I have some energy difference delta E1. Okay, here also I have some energy difference delta E2. Okay, then delta E1 is more than delta E2. Okay, that means energy of K alpha is more than energy of L alpha. Okay, consequently wavelength. Okay, then lambda of K alpha is going to be smaller than lambda of L alpha. Okay, and based on this property, very interesting problems are asked. Okay, let's do a few problems based on this property. Okay, very interesting problems like this. Okay, question. Okay, it's like this. Okay, I have this kind of spectrum, X-ray spectrum. Now the question is, this is a first peak, this is a second peak. Peaks correspond if peaks correspond to K alpha and K beta. Okay, or let me write just like this, peaks, that's it. Peaks correspond to K alpha and K beta. Identify them. What do you think? I have two peaks. Which peak represents K alpha, corresponds to K alpha, and which peak corresponds to K beta? It is given. Somehow I know. I know this. Somehow I know that out of these two peaks, one is K alpha, other one is K beta. So whichever has higher energy, K beta, this is K beta, it has higher energy. Its wavelength is going to be smaller. Okay, so the peak corresponding to the smaller wavelength will correspond to higher energy. K beta has higher energy. Okay, so this will become K beta and this will become K alpha. That's how questions are asked. Okay, if I ask you one other question, peaks correspond to K alpha and L alpha. Now what do you think? Peaks correspond to K alpha and L alpha. Identify which peak is for K alpha, which is for L alpha. Okay, if you refer to this figure, it will become immediately clear. This energy difference here, it corresponds to L alpha. This energy difference is smaller than this energy difference. As we go away, the difference decreases. The difference decreases. Okay, as the states become higher, the difference between energy decreases in subsequent levels. Okay, difference here is here corresponds to L alpha. This is smaller than this K alpha. Okay, that means K alpha has higher energy. K alpha has higher energy as compared with L alpha. So K alpha will have lower wavelength. So this corresponds to K alpha and this corresponds to L alpha. Okay. Now one other very interesting question. Okay. You try to find out answer on your own. Okay. Till now I have not said anything. You try to find out answer on your own. Okay. It's like this. Okay. Another question. Okay. Question is like this. This is a lambda wavelength. This is intensity. Okay. It's something like this. Okay. Let's say this is one spectrograph. Okay. And this is another one. Okay. This is peak one, and this is peak 2. Now this corresponds to a spectrograph, X-ray spectrograph of target metal having atomic number Z1. Okay, and this is for Z2, Z1 and Z2. Okay, you understand this? Now the peaks correspond to K alpha of two metals having two metals of atomic numbers Z1 and Z2. Okay, which metal? Okay, which of following? Okay, let me put it this way. Which of following is correct? Okay, first option, Z1 is Z2. Second, Z1 is less than Z2. And third, Z1 is more than Z2. Okay, can you figure out? And let me remind you again, if you are having trouble understanding all this, that means you have not done Bohr's atom. Okay, Bohr's atom, that chapter on Bohr's atom is a prerequisite for this chapter. Okay, we are not explaining everything, we are directly using the result. We are using direct result from Bohr's atom. Okay, now what do you think? What will happen? What do you think? Which one is correct? Okay, so I have this two spectrograph, X-ray spectrum for two different metals, Z1 and Z2. Okay, both peak correspond to K alpha. Both correspond to K alpha. K alpha for one metal here, first metal, K alpha for the second. What will be relation between their atomic numbers? Which one will be higher or lower? Okay, that we can understand. Okay, did you get the answer? Let's try to understand. Okay, energy of a shell. Okay, energy of a shell is equal to minus of, we write it like this, minus of RHC, okay, Z square over N square. Okay. Now, lambda, here it is lambda 1, here it is lambda 2. Okay. Lambda 1 is smaller than lambda 2. That means E1 is more than E2. Okay. So this photon has more energy. Its wavelength is smaller, energy will be higher. Now, this energy is proportional to, everything is constant. Everything is constant. Okay. I am comparing two metals. So only Z1 and Z2 are different. The transitions are same. Transition is happening from 2 to 1. In both cases, it is K alpha. K alpha will correspond to this. So these N numbers are same for both the states. Transition is happening from 2 to 1. Okay. So all of these things is same. Do you understand this? That means it will be proportional to Z square. Okay. If atomic number is more, energy is going to be more. Okay, the difference in energy. Okay, the difference in energy delta E is going to be equal to RHC Z square. Okay, 1 over 1 square minus 1 over 2 square. Okay, this will be energy of K alpha. What do you think? Approximately. This is just approximate. Here also it is just approximate. Why it is approximate? Why not exact? It is because this was derived for a hydrogen atom. Hydrogen atom. Okay, we are just forcibly using this relation for this metal here. Okay, it is not going to be applicable. This is applicable only for a single electron atom, only for hydrogen-like atom. This is a metal. Many electrons it has. Okay, so this relation is not going to be applicable. First thing that you have to understand. But still, just to get some idea, okay, we are using this relation. Okay, we are not going to get exact answer. We are going to get just approximate answer. Okay. So so even though it is not exact, but it will be approximately close to that. Okay, it is not going to be exact. Anyway, so RHC is constant. These two are constant for both metals. That means this energy difference, the energy will depend on Z square. Okay, higher the atomic number, higher will be the energy of these K alpha protons. Okay, so whichever energy is higher, it corresponds to higher atomic number. Okay, so that means Z1 will be more than Z2. Okay, so these are just relations. Okay, just relations. What about the exact value of wavelength and frequency? Okay, what about it? Okay, let's okay, let's do it. Wavelength frequency of characteristic X-ray. Okay, it is given by Mosley law. Mosley's law. Okay, so what he did was he derived empirical relation. Because what he did was he plotted atomic number. Okay, so he prepared target metal for different metals having different atomic numbers. Then he plotted this under root of mu. Okay, this is under root of frequency. Under root of frequency graph, and he got a graph something like this. Okay, something like this. Okay, so when he plotted the graph between using the data, observational data. Okay, at that time there was no Bohr's theory. Okay, all of this was discovered before Bohr gave his theory. Okay, so he used the observational data and then plotted this graph between under root of frequency and this atomic number. He got a straight line, and then he expressed it in this relation: under root of mu, under root of frequency is equal to A and Z minus B. A and Z minus B. Okay, here this nu is frequency. It is frequency. Z is atomic number. Atomic number. Okay, A and B, positive constants. Okay, depending on, okay, they depend on transition. Okay, for example, K alpha, K beta, L alpha, etc. Okay, so each type of transition, whether it is K alpha, K beta, K gamma, L alpha, L beta, whatever it is, each type of transition is going to have a set of values for A and B. Okay, so for K alpha, I am going to have certain value for A and certain value for B. Similarly for K beta, for K gamma. Okay, it does not depend on metal, okay? They depend on transition, okay? Not on metal. Not on metal. Okay, note this down. Okay, so K alpha for every metal is going to have same value of A and B. Now what will be value? We are going to see it, okay? We are going to derive actually. K beta of all the metals, any metal, is going to have some value for A and B. It will be fixed for K beta for all the metals. Okay, do you understand this point? Understand it very, very clearly. It is going to be confusing in exams. Okay. So this is what he derived empirically, empirical relation, based on data only, no theory. There was no theory, there was no Bohr's model in those times. Okay. Now, using Bohr model, once the Bohr model was proposed, Bohr proposed his theory, then people tried to relate it with this equation here, and they found one correspondence. Okay, let's try to see. Okay, how Bohr can also give us information about frequency of this emitted characteristic X-rays. Okay, let's see. Okay, now for a single electron, for one electron, that is hydrogen-like system, okay, energy of nth state is equal to minus of RHC, okay, minus of RHC and Z square over N square. Okay, Z square over N square. What is this? This is energy of N state of a hydrogen-like atom, hydrogen-like system, or let me say hydrogen-like atom. And it is only for hydrogen-like atom. Okay, now what if I had many electron atom, like this metal, okay, for many electron atom, okay, this En is roughly equal to minus of RHC, okay, Z effective square over N square. Z effective. What is the meaning of Z effective? Okay, Z effective is equal to Z minus B. Okay, B is known as screening constant. What is the meaning of a screening constant? Okay, let's say that I have this hydrogen-like atom. Okay, it has a certain atomic number. Let's say that it is Z. So this charge will be plus Ze. Charge of the nucleus. Number of protons is Z. Now, if I have this hydrogen-like atom, one electron atom, then this is my orbit. Okay, I have a single electron. That's it. Now this single electron is directly facing the nucleus. I have a single electron, it is directly facing the nucleus. Okay, so now this will experience the full charge of nucleus. Okay, now what will happen if I have many electrons? Let's say that I have this nucleus here. This is the first orbit, this is the second orbit. Okay, now I have two electrons here. Okay, let's say one electron here and the other electron here. Two electrons. And then I have the few electrons here. Many electron system. Okay. 8 electrons here. Now, this is plus Ze. Now, think with respect to this electron. This electron is directly in front of this. Okay, so it experiences the full charge of this nucleus. That will be Ze plus Ze. Now think about this. Now for this electron, this nucleus, this positive charge is shielded. It is covered why I screen off these two negative charges. Okay, so for this electron, the electron in this shell here Z effective is going to be Z minus 2. Okay, this does not experience the full charge of nucleus. It is screened in between this and this. Now I have two negative charges. Okay, so the effective charge for this will decrease. This is known as Z effective. Okay, so for this it becomes B becomes that means this is screening constant, B becomes equal to 2. If I have two electrons here, okay, now if I have one vacancy, okay, let's say that I have one vacancy here. I have one electron here, one electron, but here I have a vacancy. Here I have a vacancy. There is no electron here. I have only one electron. That means there is a vacancy in K shell. This is K shell. This is K shell, L shell. Now for this electron here, what is the effective charge on nucleus? It will reduce by 1. It will reduce by 1. So Z effective becomes Z minus 1 here. Okay. So this will become B is equal to 1. B is equal to 1. Okay. Now for K alpha, okay, for transition from N1 to N2, okay, delta E is going to be equal to RHC, okay, RHC Z minus B square, and then I have one N1, N2 square minus 1 over N1 square. All of this we derived in the previous class. That's why we are doing it directly. Okay. Do you understand this? Okay. Now, okay. For K alpha, okay, that is N1 is equal to 2, N2 is equal to 1. Okay. For K alpha, H nu is equal delta E is equal to H nu is equal to RHC Z minus B Z minus 1 square. Okay, this is the transition happening from L to this vacancy here. So for this electron which is in transition, for this electron, what is the effective charge of nucleus? The nucleus is shielded. Between this and this, there is one electron here. So effective charge decreases by 1. That is known as screening constant. Okay. So B becomes equal to 1. So this is B equal to 1 here. And then 1 over 1 minus 1 over 2 square. Okay. So nu is equal to 3 by 4, 3 over 4 RC Z minus 1 square. Okay. So under root nu is under root of 3 RC over 4 and then Z minus 1. Okay. Now compare this with Mosley law. Mosley law. What it says? Under root of nu is equal to A and Z minus B. Okay. That means for K alpha, A is under root of 3 RC over 4. Okay, 3 RC over 4, and then this becomes Z and B becomes equal to 1. For K alpha, okay. Now, first question, very first question. Is this exact? This is not exact. This is just an approximate value. For example, this basic premise here, this itself is not correct. This itself is not correct. This is only approximate. Because this Bohr theory is applicable only for one electron system. For many electron system, it is never applicable. Whatever we are doing is just an approximation. Okay, and we are doing it only for K alpha, only. Okay, for other transitions, okay, note down, for other transitions, for okay, like K beta or L alpha, etc., etc. For other transition, it's very complicated. It's very complicated and is determined experimentally. That's it. Experimentally. We do not bother about deriving all these things. Okay? Do you understand this? Okay, you understand this? Now, so this term here relates with energy. You see, this is coming from energy here, this term. Okay? So this term here it relates with energy, and this is it relates with screening. Okay. This is screening. So that means for different transitions, both are going to be different. For different transition, A and B both are going to be different, very complicated. Okay. Okay, we do it experimentally. We never bother to derive all these relations. But for K alpha, even though it is not exact, but it at least gives us some approximate value. Some approximate, and this is what you have to remember. Okay, you must remember this thing. Sometimes in exams they directly ask it. What is the value of A and B in Mosley relation? Okay. So that's about it. Mosley law. Let's do few problems and then we can complete this chapter. Okay. Let's just do few problems and then let's complete it in one lecture itself. Okay. It's a very short topic. It can be completed in one lecture. So let's do that. Let's complete that. Okay. Let's complete. Okay, let me write few questions and let's complete it. Okay, it's like this. Question. Okay. An alloy contains two metals. Okay. Spectrograph, X-ray spectrum of alloy contains two K alpha lines. Okay, 169 picometer and 196 picometer. Okay, alloy contains two metals, X-ray spectrum of alloy. Okay, two K alpha lines, 169 picometer. Okay, now if 196 picometer line belongs to cobalt, Z is 27, then identify the other metal. Okay. Okay, do this problem. It's very, very simple problem. It is directly based on the concept, okay, that we just discussed, Mosley law. Okay. Second, K series spectrum. K series X-ray spectrum of a metal contains 0.04 picometer, 0.0248 picometer, and 0.02 picometer lines. Okay. Okay. Now, if ionization energy of K shell is 80 kiloelectron volt, then what is energy? What is ionization energy from L, M and N shell? Okay, a little difficult. It's not challenging, but this is something which requires you to think a little bit harder to answer this. This you can answer directly, just applying the Mosley law. Okay, but for this there is no formula. Okay, you will have to think over it. You will have to think it. Then only you can answer. Okay, so do these two problems. Then we are going to do few more, and then that's it. We conclude the chapter. Okay. This chapter, I think this is the only chapter in this entire course which we are going to conclude in one lecture itself. Okay, maybe it is 1.5 lecture, 1.5 hour, but that's fine. In one lecture itself, it's concluded. Okay, you can also be relaxed. Okay, just one lecture. That's it. Okay, but you see, but in the problem sheet, you are going to find many problems. Okay, here we are not doing problems which are very easy, which are directly based on formulas, directly based on properties. Okay, and those problems I have given in problem sheet for your practice. Okay, and I'm sure that you will be able to solve all of those problems. Okay, here we are doing just few problems, problems which require something other than formulas also. For example, this problem here. Okay, here you will have to think how to solve it. Okay. So let's do this, okay, and then you will try problems from the problem sheet. Very interesting problems you will find, okay, and then if you are having any difficulty, we are going to discuss it anyway, okay, during discussion. Okay, let's see. Let's look at this. The first question here, Mosley law. Okay, under root of nu is equal to a z minus b. Okay, we are talking about k alpha lines. K alpha line. B and A both are going to be same. Okay. They depend on transition only. For K alpha, I will have some value of A and B. For K beta, some different values. But those values will not depend on metal. No matter what is the metal, I am going to have same value for A and B both. Okay. Now, this I can convert into in form of wavelength. Okay, I can use this relation. Okay, speed c is equal to nu times lambda. Okay, speed is frequency and wavelength. Okay, so this I can write as this nu is c over lambda. Okay, so this is, it's like this, under root of c over lambda is a times z minus 1. B is 1. Okay, or let me write it as b. That's fine. Now I have two metals here. Two metals. Okay. So I can write it like this. Okay. Under root of c over lambda 1 and under root of c over lambda 2 is equal to a z1 minus b and a z2 minus b. Okay. So I have this under root of lambda 2 over lambda 1 is equal to z1 minus b over z2 minus b. That's it. Okay, now here let's see which line. 169, it belongs to 27. Okay, so let me write. So let's say that z1, is 27. Okay, so lambda 1 under root of lambda 1 will be 196 here. Okay, this belongs to z1. Okay, this will, and the other one I have to find. z1 is 27 minus 1 over z2 minus 1. Okay, so here I have here 13 over 14 is equal to 26 over Z2 minus 1. Okay, now that means if I multiply it by 2 here, I get Z2 minus 1 is 28, Z2 is 29. The other metal is 29, that is copper. This is copper. That's how we can identify metals using spectrum, X-ray spectrum. Okay, a very common technique, used. It is used extensively in industries and detection and all that. Okay. Now the second one is little something which requires little thought. Okay, you will have to think. K series. What is the meaning of K series? K alpha, K beta, K gamma. K series. The meaning of K series is I have three lines are given. First line, second line, third line. Okay, so they will correspond to K alpha, K beta, and K gamma. Okay, you understand this? Now it's like this. I have this K. This is my K. Okay, this is L. This is L. K, L, M, and this is N here. This is N. Okay. Now from L to K, this will be K alpha. Okay. From M to K, okay, this will be K beta, and from N to K here, okay, this line here is K gamma. Which one is going to have more energy? Which one is going to have more wavelength, less wavelength? These are the wavelengths corresponding to these lines. Okay, K alpha, K beta, and K gamma. Okay, let me write it like this. This is K beta here, and this here is K alpha. Okay. Now, what will be their wavelength and what will be their energy? Okay. Which is going to have more energy? K gamma is going to have more energy. That means it is going to have a smaller wavelength. Smaller wavelength. That means this wavelength here, it corresponds to K gamma. K alpha is going to have minimum energy. It is going to have maximum wavelength. Okay. So this will become lambda. This will become 0.04 picometer. This will become 0.0248 picometer. And this becomes 0.02 picometer. Okay. What is energy? Picometer. Okay. 1 picometer is 10 power minus 12 meter, and 1 nanometer is equal to 10 power minus 9. 10 power minus 9 meter. Okay. So this I can write as 10 power minus 9 and 10 power minus 3, okay, meter. Okay. Now this becomes 10 power minus 9 meter. Okay, this becomes 10 power minus 3 nanometer. 1 picometer is 10 power minus 3 nanometer. Okay, do you understand this? That means this is going to be equal to, this is picometer. I want to convert this into nanometer. This is 2 and 10 power minus 5 nanometer. Okay, understand? Let me write it here. Let me write it separately. Let me write this separately here. Okay. So this is K alpha, this is K beta, and this is K gamma. Okay. Let me write the wavelength. Okay. Wavelength here and energy. What is wavelength for K alpha? 0.04 picometer. This is going to be equal to 4 into 10 minus 5 nanometer. Okay. And then this is 0.0248 2.48 picometer. This is 2.48 and 10 minus 5 nanometer. Okay, makes sense. And K gamma is 0.02 picometer. This will be 2 10 minus 5 nanometer. What about energy? This is 1240 over 4 and 10 minus 5 electron volt. Okay, is that right? Okay, that means, what it means? That means this is 310 into 10 power 5 electron volt. Okay, is that right? Okay, am I doing it all right? Or something? Okay, 1 picometer, 10 power minus 12, 10 power minus 9, 10 power minus 3 meter here. This becomes nanometer, 10 power minus 3 nanometer. I hope that I am doing it all right. Okay. What is this? This is the relation that we derived in wave particle duality. We are making direct use of this. Okay. Now, so this becomes 310 into 10 power 5 electron volt. Okay. I think we are making some mistake here. Okay. No, I think. Okay, so a big mistake. Okay, I'm making a big mistake. Okay, what is the? Okay, let me do it here. Big mistake. Okay, what is the big mistake? These are not picometer. They are actually nanometers. Okay, they are actually nanometers. They are not picometers. They are nanometers. Okay, it is nanometer here, nanometer. This also is nanometer. Okay, so all this is not required. Okay, so this is one mistake I made. Okay, let me correct it. Okay, so all of this is nanometer only. No need to convert because the energy is going to be very high. Okay, it's very high as compared to this value here. So either I need to change this or this. Okay, so this is a general value, common approximate value for this kind of transition. So this corresponds to the actual value. Okay, so that means I need to change this. So this, all of this is nanometer. This is nanometer here. Here it is nanometer. Here also it is nanometer. Okay, so now it should be fine. It's like this here. Okay, so this is 1240 over, this is 4 into 10 minus 2, this is 310 into 10 2, this becomes 31 kilo electron volt. 31 kilo electron volt. Okay, now this will be 1240 over, okay, 2480 and 10 power minus 5. 10 power minus 5, okay, 2480, 10 power minus 5. This becomes, you see, this becomes 0.5 and 10 power 5, it becomes 50 kilo electron volt. 50 kilo electron volt, okay. Then here, this becomes 1240 over 2 into 10 minus 2, this becomes 620 into 10 power 2, this becomes 62 kilo electron volt. Now what are these values? Okay, these are the energy differences. Okay, this is corresponds to K alpha. K alpha energy is 31 kilo electron volt. That means the energy difference here, this energy difference is 31 kilo electron volt. Okay, now similarly for the others also. Now what about this data? Ionization energy of K shell is 80 kilo electron volt. Okay, what is the meaning of ionization energy? Energy required to remove one electron from the ground state. K is the ground state. Okay, generally we have this confusion, okay, between ionization energy and binding energy. Okay. Both have roughly same meaning, roughly same. Generally Generally, when we remove electron from the ground state, from the first orbit here, that is known as ionization energy. Okay, and if we do it from any other state, then that is known as binding energy. Okay, but then the boundary is very it's not so clear cut. Okay, so these two terms are used interchangeably. Okay, that's allowed, that we can do. Okay, so let's forget about this difference between binding energy and ionization energy. Let's treat both as same, and then let's solve this problem. So the ionization energy of K shell is 80 kiloelectron volt. That means to send an electron from K shell to infinity here. Okay, this is infinity. This is 0 electron volt. Okay, to send an electron from here to here, I need to supply 80 kiloelectron volt. That means energy of this state, K state, is minus 80 kiloelectron volt. Minus 80. Okay, now the energy of K alpha. What is K alpha? It occurs because of transition from L to K. Now this energy is 31 kiloelectron volt. Okay, this is 31 kiloelectron volt. That means energy difference between these two is 31. Okay, so what will be this energy? It should be minus 49 kiloelectron volt. This is higher energy, this is lower energy. Okay, so when electron jumps from this state to this state, a photon of energy equal to the difference. What is the difference? 31 kiloelectron volt. A photon of this energy will be emitted. That photon is K alpha photon. Okay, now energy of K beta photon here is 50 kiloelectron volt. Okay, this is 50 kiloelectron volt. Okay, so that means this is the energy difference between here and here. It should be 50. Okay, that means this becomes minus 30 kiloelectron volt. Okay, now here it is 62 K gamma. It is 62 kiloelectron volt. So what should be energy here? What should be energy here? The difference between this and this is 62. So this energy must be minus 18 kiloelectron volt. What are these? These are energy of the different states. Okay, and if I want to find ionization energy from L, M and N shell, my electron is here in L shell. I want to make it free. I want to send it to infinity. How much energy is required? It will be 49 kiloelectron volt. This will be 49 kiloelectron volt. So this becomes ionization energy of L shell. What about M? I want to send electron from here to infinity. I need to supply 30 kiloelectron volt. From N shell here, okay, I will need to supply 18 kiloelectron volt. These are ionization energies from different shells. Okay, and if I ask you, what will be energy of L alpha photon? What will be energy of L beta photon? This is L beta photon. What will be energy of L alpha? Equal to this difference. What is the difference? 19 kiloelectron volt. Okay, it's so obvious. There is no need to solve it. It's obvious. What is the energy of L beta? This is L beta. Okay, this will be equal to the difference. It is how much? 31. This will be 31 kiloelectron volt. Okay, and then what will be energy of M alpha? Okay, this is M alpha. What it will be? It will be equal to the difference between these two. It will be equal to 12 kiloelectron volt. Okay, do you understand this? Okay, so should we conclude? Let's conclude, or let's do one more problem. Okay, that's it. Let's complete this chapter. Just one last problem. Okay, and then chapter will be complete. Then you should attempt a few more problems from the problem sheet. Okay, then you will become confident. You will become an X-ray expert if you are able to solve all the problems from the sheet. Okay. Okay, and X-ray. What is minimum wavelength of X-ray? Okay, produced from a tube operating at 40 kilo electron volt. Okay. Now, one last problem here. Okay, what is effect on following if accelerating or operating? Okay, both are same. Operating voltage is increased. Okay, first lambda naught, lambda 1, lambda 2. Second, okay, lambda 1 minus lambda naught, lambda 2 minus lambda naught, lambda 2 minus lambda 1. Different, these are the wavelengths. This is some X-ray spectrum of any metal, some metal. It is produced, it is developed at certain operating voltage, some voltage. So I am getting this minimum here and these two lambda 1, lambda 2 corresponding to these two peaks. What will happen if accelerating voltage or operating voltage is increased? What will be effect on these quantities? Just the effect means they will remain constant or they will increase or they will decrease. Just this, okay? And just these two problems and we are done with this chapter, with this lecture and this chapter also, okay? Now, minimum wavelength. What is the significance of minimum wavelength here? Okay, this is the minimum wavelength of continuous X-ray. Continuous X-ray is produced when electron loses its energy, loses its kinetic energy. Now, when all of the energy is lost in one photon, okay, then a photon of maximum energy is created. Energy is maximum, that means the wavelength is minimum. Okay. Now, so this we write it like this: Hc over lambda is equal to kinetic energy of electron. It is equal to E times V. Okay. Now, what is E times V? Kinetic energy of electron, or let me write it like this. Okay. Let me write it like this. Okay. Energy of photon is equal to kinetic energy of electron is equal to E times V is equal to 40 kilo electron volt. Okay, from a tube operating at 40 kilovolt, not electron volt. It is 40 kilovolt here. That's a mistake. That is a mistake. So the tube, the accelerating voltage is 40 kilovolt. So electrons will be accelerated. They will gain kinetic energy. How much kinetic energy? 40 kilo electron volt. The same, okay. This is 40 volt accelerating potential difference 40 kilovolt. The kinetic energy will be 40 kilo electron volt. Okay. Then what will be lambda? Lambda, it will be equal to 1240 electron volt nanometer over 40 into 10 power 3. this is electron volt. Okay, this will be equal to 31 and 10 minus 3 nanometer. Okay, this will be 0.031 nanometer. Okay, if you are having difficulty in how I am writing all this, that means you have not done your chapter on wave particle duality. In wave particle duality, we derived this relation and then we are using it directly. Okay. Now, what will happen if V increases? If V increases, okay, then this is delta minimum. Okay, delta minimum, it will decrease. Okay, so we can answer this second question directly based on this property. K alpha, the peak, these characteristic X-rays, they are property of metal. They are property of metal. It depends on transition, the energy difference in those transitions. This does not change. It is independent of accelerating voltage. Accelerating voltage can only change this value here. If I increase the accelerating voltage, electrons of more energy will be produced. Then the photon, and if all of that is converted into a single photon, okay, then photons of lesser wavelength will be created. Okay, so this wavelength is going to decrease. So if accelerating voltage increases, okay, if V increases, then okay, what is effect on lambda naught? Okay, it decreases. This decreases. Okay, now my line will start somewhere from here. It decreases further. Okay, what about lambda 1 and lambda 2? They are constant. They do not depend on accelerating voltage. They are property of metal, the target metal. Now, if this decreases, that means this gap has increased. This gap has increased. Okay, so lambda 1 minus lambda naught, this increases. Similarly, lambda 2 minus lambda naught, this also increases. Now, when these two remain constant, their difference also remains constant. Okay, in the problem sheet, you are going to find few problems based on this property. This is shifting here. Okay, so look at those properties, look at the problem sheets, solve those problems. If you are having any difficulty, we are going to discuss it during discussion. Okay, all of the problems that are little difficult, that require discussion, we are going to do that. Okay, so let's conclude here.